In this video, we'll be using Altium Designer to design a very simple breakout board for a sensor. We'll then generate all the necessary manufacturing files and assembly files for JLCPCB.com, who are also sponsoring this video, to have the PCB manufactured then also assembled by them. I'm going to be checking out their PCB parts library and then seeing what kind of sensors we might want to use. I've actually decided to go with an MPU 6050, which is a very common inertial measurement unit. That is, it contains gyroscopes and accelerometers. It's a 3-axis, and we'll make a little breakout board for this. This is something that a lot of companies such as SparkFun and Adafruit do, and why not do it yourself if you have the means. Thanks also to Altium for sponsoring this video. If you follow the link in the description at altium.com/yt/philslab, you can get a free trial for yourself to see what Altium is all about, and I'll show you a bit more about Altium in this video. On another note, I'm actually designing an FPGA board which can be used for robotics, control, signal processing, UAVs and so forth, and this is based on the Silent Zynq platform, so a system on chip containing a dual-core ARM Cortex processor as well as an FPGA on a single IC. I have a survey for this and I'll leave a link to it in the description below. You can read what this board is about and how I'll be releasing it, and possibly also the course will be on this, which I hope to release sometime next year. It's taking me a bit longer due to quite a lot of work going on, but I'm still on it. When designing a little breakout board, if I want to incorporate something like this on one of my PCBs, the first place to look is of course the datasheet. And at JLCPCB they luckily link it directly. You click on that, you can see the whole datasheet. And you can see there's about 52 pages, and only some of this is useful for our PCB design. For example, on page 21, we can see things such as the pinout. So we might have power pins, ground pins, I2C pins, and so forth. This is useful when we're creating our schematic footprints and symbols. Something that's really helpful, and that's typically included in almost all data sheets for ICs and sensors, is some sort of typical operating circuit. So depending on if you're using I2C or SPI, in our case, the MPU 6050 only supports I2C, I believe. We'll have the sensor itself connected to some various bypass capacitors, and we have various signals we might need to connect to a header. They also give you some recommended types of capacitors and their voltage ratings and so forth, and this is something we'll take over into Altium to make our schematic. So let's go there now. So here I am in Altium Designer, and the first thing I need to do is create a project. I go to File, New, Project. Then I will select I want to store it locally. It's a PCB, default project, and I'll just give it a simple name. MPU 6050 Breakout in our case. Then click Create, and you can see on the right side here, we have our project group, and we see there's no documents added. So the first thing we need to do is add New to Project, and we would like a schematic. This creates a simple A4 schematic. You can see we have a sort of title block here, and we can put all our components that we need. You can of course add more schematic sheets depending on how complicated your project is, but one is enough for this simple breakout board. I'll also add a PCB file to this, so right click, add new to project, and click PCB. If I right click, I can rename the sheet, and I will just call it schematic, and I'll call the PCB file PCB. Then I can click up here to save all. In comparison to KiCad, with Altium you have to pretty much create your own symbol and footprint libraries, or use something like Semaxis or component library to import your footprints and schematic symbols. I have another video which I'll link to in the description which goes over symbol library, footprint library, and schematic and symbol footprint creation. I have my own library which I typically use, and I'll just import that into my project. I can import existing libraries into my project or existing files by right clicking and clicking on Add Existing to Project. You can see I've added a footprint library as well as a schematic symbol library. If I double click on my schematic symbol library, you can see I've added quite a few parts. I've added generic capacitors, for example SMD 0201, 0402, 0603, and so forth, inductors, resistors, and various ICs. The same thing for the footprint library. This contains all my footprint data. I can click 3 in Altium to change the 3D view, and in Altium the footprint and schematic libraries are linked. So every symbol also has its corresponding footprint, and various data you can see in the bottom right hand corner here. So let's go back to our schematic and add our MPU 6050. Now either you can create your own schematic symbol and footprint, or you can also go to this thing called the manufacturer part search. If I type in MPU 6050, I can see if this part has already been created for us in Altium's library, and in fact it has, which you can see by this little green symbol over here. Then I click right click, place, and I don't have to create the symbol and the footprint myself, which is really neat. So I just drop it on the schematic, and then I can continue with my design. So essentially now all I'm going to do is go over to the datasheet and essentially copy this schematic over. So I'll just need a couple of capacitors and then the right connections. I won't be using this F-Sync signal. I will be using the interrupt over here, and I'll be using the I2C data lines I won't be using the clock in or any of these auxiliary lines. Also go to the pinout and signal description to see if you can connect some of these to ground or how you can leave them floating if you're not using them. So for example, the F-Sync signal, I can connect to ground if unused. I can see that an I2C address needs to be set by this pin, and so on. And all of this is in the datasheet. So let's transfer this over to Altium. If I'd like to, for example, add a capacitor to this design, I would go to Components, then I would select my own symbol library, and I can search, for example, for cap, because that's what I called it in my library, and just drag over an 0402 10-volt rated capacitor. I can click space to rotate the component and just drop it down. The way I've done this particular library is that I have generic components that I simply have a tolerance as well as a SMD size, and every time I drag in the component, I can double click and then change the value. For example, 100 nanofarads. And this is how I would do it to make my design life a bit easier, so I don't have to design a very specific part to this component. Other than resistors, capacitors, and other components, we can also drag in or place power symbols, and this is in this bar up here. You can see this little ground net. I can right-click and place one of these items. I would like to place ground, so I can click someone on the schematic, right-click to cancel the command. I typically don't like to show this ground over here, so I just go on the right here on Properties and hide the name. I would also need a power, a 3.3 volt power symbol, so right-click, place VCC. I can click on Tab on my keyboard, and that goes into the Properties window. I change the name to +3V3. Then I click Enter, and I can move the symbol around again. Okay, so let me just transfer everything from the datasheet into Altium. Now I've copied the most basic parts of the schematic from the datasheet over to Altium. The way I drew wires is by pressing Ctrl W and just clicking, and I can just draw some wires on the schematic. Also, you can see these little crosses tells the electrical rules check to ignore these pins or these connections. I can do that by pressing P, V, and then N, and that's a generic no ERC. So all the no connect pins are not connected. All of these over here don't have to be connected. Other than that, I have a lot of decoupling on the various pins, my logic voltages, my power input, and so forth. I also have these pins over here, for example, clock in. And according to the datasheet, if we look again, clock in is an optional reference clock input, and we can connect to ground if it's unused. The address pin essentially determines this I2C slave address least significant bit, so I've also just tied that to ground. And the frame sync input, I can also connect to ground if unused. Again, this is a very simple breakout. All I'm going to be doing is connecting the SCL, SDA, interrupt, and power to a simple header. So let's add the header now. I typically like JSTGH connectors, so I actually have the footprint and the schematic symbol already in my library. I can just drag it over. I can press X and Y to flip it around the various axes. Another thing in Altium, of course, is net names. So I can press P and then N, and then Tab to change the net name. So I will call this I2C SCL, put it over here, and then Ctrl W and to connect it up to the pin. And I will just do that for all the remaining connections. So now I've added all the remaining connections. I have the I2C data lines, the interrupt, but I also, even if these pins or nets aren't connected to anything or any header, I always give any nets I have in my schematic names, and this will really help when I'm routing later, especially for really complicated projects. Otherwise, if I didn't, for example, call this net here IMU_CP out, this would have a name such as net U120, for example, and that really doesn't give any meaning when you're doing your PCB layout. Now, I2C needs pull-up resistors. This could either be on the kind of host board, but let's just add it into this board just for completeness. You can always solder these off later or add them as do not place resistors. So I'm going to search in my schematic library and add some resistors. These resistors need to be tied to 3.3 volts. I can just copy my symbol, Ctrl W to route wires, and then I'll change these into 2.2 kilo ohm resistors, which is my go-to value for I2C buses and 3.3 volts. Now we could add a linear regulator to step the input voltage coming from this connector down to 3.3 volts, but for the sake of time and simplicity, let's just assume we get 3.3 volts from this connector and ground coming from some sort of host board. What I typically like to do is some sort of pi filter, for example, for power input or power output. That's a capacitor, farad bead capacitor, and that helps with some power supply filtering. Let me just add that. So here's my pi filter connected to pin 1, which I assume is my 3.3 volt power input. Again, I give it a net name or power name, then I have a capacitor, farad bead, capacitor. And this essentially will help filtering this 3.3 volt rail. For connectors, I will typically also add some form of ESD protection. This could be something like TVS diodes. For example, I could just drag a couple in here, protect the 3.3 rail, I2C data lines, as well as the interrupt pin. For the sake of simplicity, I will leave this out, but I recommend that you pretty much always add ESD protection to your connectors. Let me just finish off this connections here. Here I've added the I2C, SCL, and SDA data connections, as well as the interrupt pin. You can see I've also put a ground connection between the SCL and SDA lines, and that helps with current returns and signal integrity, as well as EMI. I always try to place at least one ground pin next to a data pin. Let's just clean this schematic up a bit. I can do that by creating bounding boxes, by pressing P, drawing tools, and then line, and I can just draw some lines around my individual blocks. Then I can also give these little boxes some names or some labels. We just press P and then text string, and then I can write, for example, connector, and then I can write, for example, IMU over here, just as an example. I can of course place kind of a title for this, so I will just call this IMU or MPU 6050 Breakout, and then I can make the text size a bit bigger and put it at the top of the schematic here. Of course, I can also add text to this title block, like my name, the revision, and so forth, but let's just leave that out for now. Before we move over to the PCB design, we of course need to annotate this schematic. We can do that by going up here to Tools, Annotation, and Annotate Schematics. So let's do that. You can also individually just click on the designators and annotate yourself. And there we go, now we have everything annotated, all my connectors starting with J, all the capacitors starting with C, farad beads, resistors, and the IMU itself. Now we need to check the electrical rules check to see if our schematic kind of makes sense to Altium. So we can right click and click validate, and if nothing comes up, it looks like everything is fine. And we can move over to the PCB routing. I've double clicked on the PCB document, which brings up this view. At the bottom, we have our layers, so our top copper, bottom layer, we have various overlays, that is the Silkscreen, pastes, and so forth. I will be creating a 2-layer board for this very simple design, but you can also go to Design, Layer Stack Manager, and then that lets you change the layers, the thicknesses, lets you calculate impedances, and so forth. Before I import my components, I typically go to Project, Project Options, Class Generation, and get rid of these ticks of Generate Rooms and Generate Classes. Then I go to Design, Import Changes from MPU 6050 Breakout. And this will list my nets, my components, and then I can click Execute Changes, and this will import it to my PCB document. As you can see, everything has kind of appeared here. Then we can just essentially drag components around and then place them on our PCB and then route them afterwards. I want to hide some of the layers, so I'll go to Mechanical 13, for example, right click and click Hide. That gets rid of some of the information you see here and clears things up a bit. I will just use one of these layers, for example Mechanical 1, to draw my board outline, because this is a rather big PCB and we don't need something that big. I also need to change my units to millimeters, and I can do that at the bottom right here, Properties, scroll down and click on millimeters. If I press G on my keyboard, I can change my grid. I'll change that to, let's say, 1 millimeter. Then I press P, line, and I start drawing my outline. Now that I've drawn my outline, I can select it by just dragging over, then go to Design, Board Shape, define board shape from selected objects. There we go, I've defined my board shape. I can just drag my components a bit closer. And I can also switch to the 3D view by pressing 3. And you can see all the components have 3D models, even the one we used via this manufacturer part search, and so forth. And this is quite nice to just check your design. I can press 2 to go back to 2D view, and I can start placing these components. So again, I typically just drag, and I can see where my components need to go. Space to rotate, and I can place everything on this board here. So let me just do that and arrange it in kind of a nice way. So now I've arranged something on this rather too large PCB, but we'll just keep it like this for simplicity. I have the inertial measurement unit here. You can see I have some ground vias connected to the central ground pad, and all these decoupling capacitors around it that we had in the schematic, I've placed as close as I can, within reason of course, to this device. So Control M, I can measure distances, and then if I click, you can see that's about 1.5 millimeters from this pad to that pad, so very close indeed. And I've done that for all the bypass and decoupling capacitors. This Silkscreen I can just move around by clicking and holding, and then dragging. So I've placed it kind of around it. A lot of times I don't keep the Silkscreen on my boards, but something for as simple as this, and where I have the space, I'll keep it on. Things like the pull-up resistors I can place a bit further away from the device, but pretty much anywhere on the bus, either close to the host or close to the slave is fine. My Pi network is over here for the power supply filtering, and my connector is up here. If I wish to place additional silkscreen, I can go to the top overlay layer over here, or the bottom overlay layer, which is the bottom silkscreen. I can press P, and then string, and I can write some sort of text. For example, MPU 6050 breakout board. Then I can just place that somewhere where I feel is convenient. For example, over here. I can also change the font, text size, and so forth. Let me just change that into something a bit larger. I can change the stroke width, and so forth. There we go. We also might need something such as mounting holes. So you can either do that by going to the schematic and adding some sort of symbol and a footprint for a mounting hole, but you can also just go, for example, to the top layer, then press P and go to pad. Then I will press tab and I will just call the designator MH for mounting hole. It has no net. I don't want this connected to anything. And I want the layer to actually be multi-layer. So not just the top as an SMD pad, but I want it a through hole. Then I will go down and I will select my shape to be round. I want a 3mm hole and pad, and that's about it. Then I can place it where I feel good. So one over here, and one in every corner. Now that I have my mounting holes placed, I can begin with routing and putting kind of ground pores down. Again, pressing 3, I can change the 3D view. On my bottom layer, I would like to have a ground plane or ground pore, so let's do that now. Press 2 to get back to my 2D view. I click on my bottom layer, then I can press P and then G, which stands for polygon pore, and I can start drawing it. So let me just start it in the corners. Right click to finish the command, and you can see it actually doesn't have a net. So on the right side here, I go to net, type in ground, then it needs to be re-poured, and there we go. I have a solid ground plane on the bottom layer. Now let's go over to routing. In Altium, I can click Shift S to cycle through which layers I want visible. So right now I have the top layer selected, and by clicking Shift S a couple times, I can just have that visible, and this is quite helpful for routing. So let me connect up the capacitor connections first by using very thick traces as wide as the pad going directly into the capacitor connection. So let me start with that. I can do that by clicking Control W, and this starts my routing. I can change my grid to something better, 0.25mm. I can click, and this then makes me go into this routing mode. I can press Tab to change my track width, and I'll change that to something like 0.3mm, and I just click and route, and that's pretty much it. So let me just do that. So here I've just routed the main connections, including the I2C data lines. You see I go straight out and then break away immediately to keep the separation between these two data lines or clock and data lines as much as I can, or much as is reasonable. Avoid crosstalk and things like that. For power tracks, for example, this 3.3 volts, I've routed this much thicker than the data line, so it's 0.5mm. And you can see I've routed power going to the various pins and so forth. What I need to do is for every ground connection is route a wide trace out and then dig down to the bottom layer, which is a ground layer, and then that will all be connected. The way to do that is Control W to route my tracks. I want a thick one, so I will change that to 0.5mm. And then you can do P via, and I can press Tab again to change my via dimensions, and I would like a 0.7 diameter, 0.3 hole size via. And I can just place that down with left click, and that connects to the net it is placed on. And you can see that in the 3D view here. I will have to move the silkscreen around afterwards to make sure it doesn't cover the holes, but let's place all the vias first. So now I've placed all the vias, all the ground vias going to the bottom ground pore. I also have my interrupt connection, which routes down here. I go via to that bottom plane, over as quickly as possible up again on the top layer, and that routes into my interrupt pin on my IMU. I'm trying to keep this connection as short as possible as to not split the ground plane too much. So something like this is absolutely fine. Going back into 3D view, I might have to move my silkscreen around to make it a bit nicer, but that's pretty much it. Now once you're happy with your PCB design, you can go to Tools, Design Rule Check, and then run a Design Rule Check to make sure you're within all of the clearance rules and so forth. The design rules can be found under Design, Rules, and you can change all the clearances, your routing widths, wire widths, and so forth to make sure the DRC is done properly. But all that is left to do now once this DRC has passed, which it has in my case, is to then export the Gerber files, as well as the bill of materials and footprint position files for JLCPCB manufacturing and assembly. So let's do that now. Let's generate the Gerbers first. Go to File, Fabrication Outputs, Gerber X2 files. Then I would like my units to be in millimeters. I don't need the DRC rules file. And I need to select the layers I would like to plot. I would like the board outline, the legend, paste, and so forth. For pretty much all of them, which I can go down here and click used on, except the mechanical layers, which are just used for my information. So pads, copper, solder mask, legend, which is the overlay, and so forth. We don't have any legend on the bottom, and that's fine for now, so it's not being exported. I also need to export the drills, which are over here. So non-plated through holes and plated through holes. And then I can click OK. And this will plot all the files in this Camtastic editor. And I can verify my Gerber files here. So I can do right click all off and then go through them one by one to see if this looks like what it's supposed to look like. Once you're happy with that, you can zip them up and then upload them to JLCPCB, but we also need to do the bill of materials and footprint position files. So going back to the PCB, click on File, Assembly Outputs, and Generate Pick and Place files. I want my units to be metric, and I want the format to be CSV. You can see all the components listed here. Click OK. Then you can right-click on your project, click Explore, and then go to Project Outputs, and this is where the Pick and Place file is actually placed. So I can double-click on that and see what Altium has exported. I don't need the top here, I can just delete that. And then I need to make some changes for JLCPCB. All the top layers need to be changed into top. So I can press Ctrl F, replace, find top layer and replace it with top. I need to change my center X to be mid X and my center Y to be mid Y. I don't want my J1 to be assembled by JLCPCB because I believe they don't actually have it. So let me just remove that line and that would be ready for JLCPCB. I'll also just change the name of this to make it a bit nicer. I'll call this MPU 6050 Breakout CPL. Now we need the bill of materials. So go back to Altium, click on Reports, Bill of Materials. Then I would like the file format to be CSV. I have my components here. Click Export, and I will just give it the name of -BOM Bill of Materials. Save, and that's it. I can open that again. I also need to add a field called the LCSC part number, because if I go to JLCPCB.com to the parts library, you will also find this part number here, and this is what I need to transfer over into my document over here. So for example, MPU 6050 will need to have another entry with that part number. And I will do that for all the capacitors, farad bead. I'll get rid of this connector because it's not going to be placed, and the resistors. Let me just do that. So now I've updated my bill of materials to include all the LCSC part numbers. I can go to JLCPCB.com, click on Instant Quote, and start uploading my files. So I click on my Gerber RAR file or my zipped file, and that'll start uploading it to JLCPCB for analysis. So now the file has been uploaded. You can see the top and bottom views in the preview. It's 2 layers and it detected the dimensions. You can choose how many PCBs you would like, the colors, thicknesses, and so on. I typically either go for lead-free, hot air surface leveling, or ENIG, and I would like to remove the order number. Then you can click on Assembly. You want the top side assembled, 5 pieces, and tooling holes added by JLCPCB. Next, we need to upload the bill of materials and the component footprint positions. Then click Next. And here you can verify what we uploaded is actually what the automatic system matched the components with. So check the left and right columns to make sure everything's okay. Then we need to check the footprint placements and rotations. So all the capacitors, resistors, farad beads seem to look okay. We have a problem with U1, which seems to be 90 degrees off. So we need to rotate it 90 degrees counterclockwise. So going back to the CPL file, which is our footprint position file, we need to subtract 90 degrees from U1. U1 is at 0 degrees, so it wraps both 360, so we need 270 degrees. Then save and re-upload the CPL file. And now it looks like U1 is rotated correctly and everything looks okay. And you can see it's pretty cheap for about 5 of these boards and it's made all by yourself. So that's pretty cool. Then click Save to Cart and you can add other items or then also go to Secure Checkout and choose your shipping method. And that's all there is to it. Thank you very much for watching this video. If you could please follow the link in the description to fill out the survey, that would help me out immensely. And I look forward to seeing you in the next video. Thanks again.